Okay, recording is rolling. Today is Monday, November 8th. Gonna do more of these chapter 9 puzzles with you guys. We did some of these last week. We'll do almost the rest of these today. We'll get really close to the end. Then tomorrow's gonna be a weird day because I'm gonna be proctoring an exam in the morning. So, well, we're gonna make this a reading day. And that's actually a good thing for you guys because I have a new quiz for you, and this will be a great opportunity to go ahead and knock this out. You guys see attached to the right side of your desk, flip to the right side of your desk. There's a half page that says Momentum Quiz Honors. You guys see Momentum Quiz Honors? It looks like this front back. Okay. So pick that up. Now, the first few questions are conceptual questions that you guys are actually going to see on this Kahoot that's coming up a couple days from now, but some of those questions, the ones on the back, you guys should be able to do already, and a couple of those are pretty tough questions. So yeah, give you guys tomorrow to work on that. Okay. You guys know Thursday is Veterans Day, so we're not going to be at school. Okay. And yeah, thank you. I would still like to get into another lab with you guys, so try to do that too. Okay. So two things that are due coming up. And there are two things I mentioned already, but just to cover this checklist. You guys know that these Chapter 9 momentum problems, I'm picking up this Friday, and we'll almost finish these today. We'll get really close. And then this Open Notes take-home quiz is due 1 week from now, next Monday. Okay? You guys got that? All right. If you guys have any questions about other room relocations, I do have a spreadsheet here. And, I have a new poster for you guys. You guys see this one hanging in front of the room right here on the right side? Okay. So, force versus time. Here, guys, everybody look here. All right, force versus time. You guys have seen this. You guys saw this last week, force versus time. Okay. What does the area under a force versus time curve represent? Impulse. Okay. Which is a change in momentum. Okay. So impulse just for the means change in momentum. Okay. And there's two perspectives on change in momentum or impulse. Okay. One is change in momentum could be mass times change in velocity. Okay. But how do you get a mass times change in velocity? Well, you get that by applying some force for some time interval. Okay. Now here I said average force because it could well be, and this true a lot of times, that there's a variable force. I gave you guys an example last week of like a bat hitting the ball. So like the bat makes contact with the ball here and then pushes maximally against it here, and then the ball leaves the bat right at this point. Okay, now that all happens in a tiny fraction of a second, but that would be like a variable force situation. So the area of that triangle, the area between the curve and the time axis. Okay. But that represents the impulse, change in momentum. Okay. But another perspective on that is you could say, well, if say this was a block of ice and it melted, it would melt down to like this average value right here. Like say the area of that rectangle. Okay, see this rectangle? Okay. That's the exact same area using that average force, which is half of the maximum force. Okay, so average force times the time. Okay. All right. So let's take a look at where we left off last week, which is number 67. Now, how I remember this going is that we did the first few problems. We got to 67. I think I got about 2/3 of the way through this, and then the bell rang, and it was a Friday at the end of the day anyway. So let's go ahead and do this one from scratch, and then you guys can pick up the notes where you need to. So baseball. Yep. Everything. Yep.
Is this due Monday or Friday?
The take-home quiz is due Monday. Okay. So baseball. We got a 0.145 kilogram baseball moving at so many meters per second when it's caught by a player. Okay. So I'll use the mass because that's the mass of a baseball, but I'll change the initial velocity. So mass of the baseball is 0.145 kilograms. Okay. By the way, on your take-home quiz, for the baseball, I rounded its mass to 0.15 kilograms just because that's what I could fit in an Excel cell. Okay. Let's say the initial velocity of this ball is 30 meters per second. Right? And somebody is going to catch this ball. Okay. Which means, guys, if you catch a ball, what's its final velocity equal to? Here, guys. What's the final velocity? 0. Right? Here's the second. The first question says, find the change in momentum of the ball. change in momentum, delta P. Right? They could have said find the impulse on the ball, right? That'd be the same thing, change in momentum of the ball, right? Is that mass times change in velocity? Mass times change in velocity. And change in velocity is final minus initial velocity, right? Just like that. Oh, let's just pop in the numbers. Got a 0.145 kilogram mass going to 0 meters per second from 30 meters per second. With my numbers, that's going to be 0.145 times negative 30. I'm looking at negative 4.35 kilogram meter per second. Right? Kilogram meter per second. Right? So that is the momentum change of the ball. You notice it's negative. What does that mean? Well, if the ball was originally headed in a positive direction, see how V naught's positive, wouldn't you need a negative force and a negative impulse to bring it to a stop? Right? Speaking of impulse, you could also call this negative 4.35. Do you guys remember the alternate unit you can use for momentum or impulse? Instead of kilogram meter per second, you could also call it
Newtons per second.
Newton seconds. Yeah, Newton times second.
Yeah.
And this perspective is actually going to lead straight into the next couple of questions. Right? That looks like a force times time interval. Right? Newton seconds. All right. Question B. If the ball is caught and it's brought to a stop in 0.05 seconds, what is the average force exerted on the ball in 0.05 seconds? Oh, okay. What's the average force? Well, part B. I know that average force times time interval, that's supposed to say delta T, time interval, okay, is the change in momentum, the impulse, right? And we've already calculated all this stuff, and it came out to negative 4.35 Newton seconds. That was the answer to part A. Right? And they just told us the time to bring it to stop is 0.050 seconds. Right? Average force, solving for 0.05 seconds. As a fraction, wouldn't that be like 1/20th of a second? Right? Because you guys know there's like 20 nickels in a dollar. Think of it that way. Okay, so if I divide both sides by that time interval, then that will isolate the force. It's just an algebra step you guys have seen a million times in here. Okay. So negative 4.35 Newton seconds, all in 0.05 seconds. The seconds cancel. And we're looking at an average force of negative 87 newtons. Like that. That's an average force, right? Not necessarily the maximum force. Right? Remember this graph, right? We just found this right here. Average force. Guys good? Right, part C. What if instead the ball takes 0.5 seconds to come to a stop? So the difference between question B and question C is they just said that the time interval to come to a stop is increased by a factor of 10. Okay. So guys, imagine you're catching the ball, right? And maybe you're moving your hand back while you're catching it, and wouldn't that extend the time interval of that collision, right? What would that do to the force if you extend the time interval? Would that increase or decrease the force? Let's take a good look at this impulse formula. Average force times time interval is equal to, well, the impulse, right? Mass times change of velocity. Right. And we just got all this. This is negative 4.35 Newton seconds. All that deal, right? Let me divide down that delta T so we can see this relationship in terms of variables. M delta V over delta T, right? So change in velocity per time. You know what? This impulse formula, which is this line right here, isn't it just one step away from Newton's second law of motion? Look at that. F equals ma. Rate change of velocity. Isn't that what acceleration is? That's what it looks like, doesn't it? But what we're interested in is we're saying, what if you brought that ball to a stop in an extended time period? Right? Now, the impulse of the ball doesn't change between question B and question C, because, well, same mass, same initial speed, same final speed, right? The m delta v stays the same. That's your negative 4.35 newton seconds. But if you increase this time interval by a factor of 10, right? Then what's happening to the average force? It's got to be doing what? Getting smaller or decrease. If you increase the delta t, that's going to decrease the average force, isn't it? If I can further do a factor of 10, I bet the answer to this question is going to be negative 8.7 newtons. Right? Let's see if it is. So m delta v collectively is the same as it was before, negative 4.35 newton seconds. But now it's all happening in 10 times the time from question B, so 0.5. I hope this is negative 8.7. Let's see if it is. It's negative 4.35 newton seconds divided by 0.5 seconds. Seconds cancel. I'm looking at, yep, negative 8.7 newtons. So, because if you know some formulas and some numbers, of course, you could just turn your brain off and plug and chug, but that's not really like the point of the class. One of the things you're supposed to get out of a class like this is, can you understand relationships among variables? Can you read the music behind the equations? Right? Can you relate this maybe to a similar type story? For example, what if you were in a burning building on the 3rd floor and you had to jump out the window to escape? Would you rather land on the hard sidewalk or would you rather land on a trampoline? What do you guys say? Trampoline. And you know why? Because it's the exact same premise as the difference between part B and part C, right? So you'll build up some speed by the time you're about to hit the ground. Your mass is whatever your mass is. Right? Your impulse of falling, hitting the ground, coming to a stop, it's going to be the same in either the situations, sidewalk or trampoline. But the time interval would be different. Therefore, the force is going to be different. That trampoline is going to, if you hit that sidewalk, it's like, bam, come to a stop real fast. If you hit that trampoline, it goes, whoo, it extends the time interval of that collision, therefore decreases the average force. Look at that, right? Okay, number 69, a nitrogen molecule with a mass of 4.7 times 10 to the negative 26 kilograms. Okay, yeah, we're talking about like a nitrogen molecule, 10 to the minus 26 kilograms. That makes sense, right? Moving at, so many meters per second, strikes the wall of a container and bounces back at the same speed. Right? What questions we got here? What is the impulse of the molecule? And if there are so many collisions per second, then what's the average force on the wall? Well, hey, got force maybe acting on a wall of some area. You know what this makes me think of? Is maybe some kind of pressure situation. I blew up a balloon for you guys. You guys see this balloon? Show it on the video. Is there a huge atmospheric pressure pushing down on the balloon? You guys remember we talked about this before? It's what, like something like 14 pounds per square inch, something like that, right? Okay. So every single square inch is like it has a bowling ball worth of like force on it. That's what the pressure is. Right? Why doesn't this balloon just like collapse? Well, because it's filled with air. It's providing equal and opposite force on the inside, right? Balance that out. Some kind of equilibrium. Right? This question is actually going to relate momentum and impulse to stuff we'll talk about next semester, which is kinetic energy theory of temperature and heat energy. So let's get a diagram of this going on. So you got like a balloon wall, and you got this air molecule. Notice they said nitrogen because the era that we're in right now, it's actually a mix of different gases. What is the predominant gas that we're in right now? It's mostly what? Nitrogen. Yeah, it's almost 80% nitrogen. It's about 20% oxygen and like trace amounts of other stuff. Right? So we got this individual nitrogen molecule. Well, actually, it's like this looks more like this if you guys came from chemistry, but whatever. That's it. Right? 4.7 times 10 to the negative 26 kilograms. Right? And that balloon bounced off. You guys see this latex surface of that balloon? Balloon bounce off. And if it bounced off at the same speed, which the question says it does, whatever speed it's going in, same speed out. Right? So that collision would be perfectly what? Elastic or inelastic? Elastic. Okay, so the momentum and kinetic energy is conserved in the system. So if the V naught was they said 550 meters per second. So let's have left be negative and right's positive, 550 meters per second. And then V final is positive 550 meters per second. Okay. What is the change in velocity of Boing? What's the change in velocity? V final minus V initial. And it's not 0. It's what? 1100. Yes, the 1100? Okay. We'll draw a number line for you guys in case I like to think of this number line model. Okay. So suppose you have 0 meters per second here. You have negative 550 meters per second here. 550 meters per second here. If you didn't see it before, I bet you see it now, that the change in velocity is final minus initial, 1100 meters per second. You guys see that? Final minus initial. Okay, so what is the impulse that one molecule delivers to the wall? That's the first question. What's the impulse? Okay. Impulse, I could say F delta T, or I could say M delta V. And the M delta V part is going to help us now. We'll save this other part for later. Okay. But just focusing on this. Okay. I've got the mass of one of these nitrogen molecules is 4.7 times 10 to the negative 26 kilograms. Okay. And the change in velocity is 1100 meters per second. Okay. See what that multiplies out to. 4.7 by 10 to the negative 26, all times 1100. Looking at 5.17 times 10 to the negative 23, and that would be kilogram meter per second, or you could just say Newton second if you wanted to. Okay, guys got that? That is the answer to question A. What is the impulse that one molecule delivers to the wall? Or, well, I guess that's the impulse the wall delivers to the molecule being a positive number, so get the negative version of that on the wall. Is that right? Okay. And question B, if there are like 1.5 times 10 to the 23 collisions to each second, what is the average force on the wall? Average force on the wall. Right? So question B, that's where we're going to bring in, this right here, average force. Right? So average force, for solving for, times the time interval is equal to m times delta v, and we solved and got a number for that. Right? So shouldn't you just divide the delta t over? Average force is equal to the impulse, all divided by the time interval. Okay. Let's sort of set that up with dimensional analysis sort of type approach, although you could just plug numbers into that, that'd be fine. But you know that there's 5.17, give you guys a little bit different perspective how it solves. 5.17 times 10 to the negative 23. Well, it does say kilogram meter per second, but you guys know it's the same thing as Newton seconds. Right. Per collision, right, one molecule, boing, collides off the inside wall of that balloon. Okay. And then I told you here's the additional piece of information from this question. 1.5 times 10 to the 23 collisions every second. Right? You guys see collision, cancel, seconds, cancel. Got some number of newtons on the board. So what is 5.17? Before I get plugging and chugging. Guys, what is 10 to the minus 23 times 10 to the 23? It is 1. Yeah, washes out exactly. Right. If you want a little bit technical middle steps, then you could add these exponents together because they have the same base. Right. Negative 23 plus 23, that's 0. What is 10 to the power of 0? It is 1. Yeah, right from a math class. Anyway, long story short, that goes away. What is 5.17 times 1.5? I'm looking at 7.76 newtons of force. Now you can take that one more step to get to pressure. Do you guys remember what the unit for pressure is? Pressure is... Okay, yeah, PSI could be a unit, right? What does that stand for? It stands for
per.
You got pounds per square inch, pounds per square inch. That's what PSI is. Right?
Almost.
Now in this class is where you use metric system most of the time. That would be equivalent to like Newton per square meter. Right? Well, yeah, this is a conversion factor. Right? But that's what pressure is, some kind of force per area, right? So if you wanted to figure out, hey, what's the there's a bunch of air molecules in this balloon that are boing, 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 like bouncing off the inside wall of this thing and just doing like exactly what we just did. Okay? If you want to figure out something about pressure, let's say, like what's the surface area of this balloon? Might do like 4 pi r squared. I get it that way. Get the area, take this force, divide by that area. That would give you a pressure value, wouldn't it? Right? So kinetic energy theory of like temperature would say that, say if you heat this up and make it warmer, what do you think happens to the air molecules' speeds? Yeah, it would also increase, right? Probably bounce off faster, delivering greater impulse, greater force, greater pressure. And then what happens to this balloon? If I heat up this balloon, what happens to its volume? Starts expanding. Ooh. I bet that's going to tie into ideal gas law when we eventually get to it. You can remember back to, I remember the whole model with like collisions and momentum and impulse, and it's consistent. Right, number 70, rockets. Small rockets are used to make tiny adjustments in the speeds of satellites. One such rocket has a thrust of so many newtons. If it's fired to change the velocity of this thousands of kilogram spacecraft by this many centimeters per second, then how long should it be fired? Like what time interval? Okay, I see a force, I see a mass, I see a change of velocity, and we're being asked for a time interval. This sounds like it's going to fit right into the impulse equation, doesn't it? Contextualize some of these numbers. 35 newtons. Guys, your guys' heaviest lab weight weighs how many newtons about? Yeah, okay, so 1,000 grams of mass, right? And how many newtons of weight is that? Yeah, like about 10 newtons. It's like 9.8 newtons, but a lot of times they call it pretty close to 10 newtons. Okay, so if you had like 3 or 4 of these, that's the thrust force we're talking about, like 30 or 40 newtons. Okay. And anytime I give you guys a car, for an example, and in my notes I usually make the car in the ballpark of about 2,000 kilograms. Okay, so this looks like about 30 or 40 cars. Okay, so we've got the spacecraft floating around. It's got about 3 or 4 of these worth of thrust force. And it's trying to move like several dozen cars. Interesting. So to speed it up or slow it down by say like this much, I wonder how long those thrusters would have to fire for. That's what we're trying to figure out. So zoom out. Right, so force thrust. I'm going to make up my own numbers for the notes. I'll round it down a little bit, say like 30 newtons. Say mass of the craft, like maybe this many kilograms. And let's say the delta V we're shooting for is like 75 centimeters. Ooh, they did centimeters per second. Can you guys convert from centimeters per second to meters per second? How many meters per second is that? Yeah, 0.75, right? So careful about that. So when you start feeding numbers into equations, make sure that the units are consistent with what you're trying to find. I'm going to use this version right here, meters per second. Right, so my numbers are different from the book numbers, but not that different. So the answer should be similar order of magnitude. Right? So we're looking at force times time interval, which we're solving for, time interval, is equal to mass times change in velocity. Right? Just like that. Okay, so plug some stuff in. About 30 newtons of force for some time interval. And that's going to result in a big old spacecraft, so many kilograms, changing its velocity by this many meters per second. True? All right, pause before I go plugging and chugging. On a graph like this, like your guys' new poster, right? We are looking truly at a rectangle, right? So we're going to have like a constant force, right, applied for some pretty good time interval, right, which we're solving for, so that there's an impulse that results from that, right? We're just focus on this here rectangle, right? Because this would be a rectangle graph. You guys see the one algebra step? I have to divide both sides by what? 30 newtons. Oh yeah, 30 newtons. Yeah. Cancel out on the left side, and time interval is, okay, what's 70,000 kilograms? That's 0.75 meters per second, divided by 30 newtons. Look at that. Ooh, time interval is a crazy number of, what is that? 1750 what? Seconds, right? Seconds? Okay, we need thousands of seconds. Ugh, what the heck does that even mean? Maybe for like human context, we better put this in like minutes or hours, something like that. All right. Can you guys do dimensional analysis and convert that into minutes? Help you guys out here. Convert that into minutes. Because I know there's 60 seconds in 1 minute. So let's say 1750 seconds, 60 seconds per minute. Look at 29 minutes. 29.17 minutes. Subtract 29 times 60. You could call that 29 minutes and 10 seconds. That's exactly how long you got to fire those thrusters to reach your goal. All good there? All right, number 78, skateboarding. Got Kofi with the mass of so many kilograms is riding a skateboard with the mass of very small mass, just a couple of kilograms, right, traveling at this many meters per second. Kofi jumps off the skateboard and and the skateboard stops dead in its tracks. Ooh, in what direction, with what velocity did he jump? Let's get a picture going for this and then figure this out. 78, Kofi on the skateboard. All right, so like normal, I'll change my numbers a little bit from the book numbers, but not a whole lot. So order of magnitude, the answer should be the same. Okay. So we're gonna have a before and after photo of what happened with those skateboards. Okay, so before, right, here's Kofi on the skateboard, and then after Kofi is jumping off this thing. Oh, I should have asked you guys which way does he jump, but because they're collectively moving forward together with some v naught. Okay. And then afterwards, the velocity of the skateboard, well, let's say velocity skateboard, because would be 0. Then doesn't it make sense that Kofi had to jump forwards so that he pushed the skateboard backward to a stop? Right, kind of like that. And then, what is the final velocity of Kofi? I always call it Visa K velocity Kofi, right? That's what we're trying to solve for. Right? I do have to throw some mass values up here. So let's say mass of Kofi is gonna make up my own number. I'll call this guy 50 kilograms, okay. And the mass of the skateboard I'll call 3 kilograms. Okay. You guys read that? How fast? What is V sub K? You guys good so far? All right. So we've got before and after, right, the jump. Right. Now, some other things. So let's think about the big picture of what's going on with this problem. There are actually 2 different interpretations of what this answer could be that would lead you to different numbers. Okay? There's maybe a complicated interpretation and there's a simpler interpretation. The complicated one is, what is this actual true jumping speed? Right? Like if you were to stand on ground with the push with the same force, yada yada. Right? The reason that was a little bit more complicated is because it, well, you have to consider that what would be subtracting from it is the fact that he's pushing the skateboard back at the same time. Right? The more straightforward interpretation of this, and the one that I'm going to do with you guys, is suppose that there is a third-person observer, maybe this guy over by this still tree. And he's got a radar gun. He's pointing a radar gun. He's from an inertial frame of reference in the background. Right? From this guy's point of view, then this is actually a much more straightforward problem. So that's the interpretation we're going to take you guys through. Okay? So we got our conservation of momentum. sum of momentum before the jump is equal to sum of momentum after the jump. Right? Okay, now before I get plugging and chugging, I want to remind you guys like why we are doing this method specifically, right? Like, why not a different method? Because one thing you guys have seen throughout this class is that sometimes there's multiple ways to approach things, and they should all lead to the same answer, right? Why not do conservation of energy? Right? What if we did do, say, like energy conservation? You would get the wrong answer, but maybe I should ask a question like this: where is there more kinetic energy, before the jump or after the jump? Where's there more kinetic energy? After, yeah, because him jumping, there's like energy coming like from his muscles in that jump. It's like he's adding energy to that system. Now I can make up whatever numbers I wanted to, and I guarantee you that kinetic energy will be more after compared to before. We'll even test that after we actually solve this problem. Right. Also, if you film this whole thing and you ran it in reverse, wouldn't it look like he jumps on the skateboard and right, like an inelastic collision? In fact, that's exactly what we're going to use in inelastic collision in reverse. Just like want to throw in the baseball on Magic School Bus frictionless field, just like that grenade exploding, same thought process. We're going to have a combined mass of Kofi plus skateboard, all moving with some initial velocity. Right? And then Kofi's going to jump, which is going to add mechanical energy to the system. Right? That's okay, because momentum is still going to be conserved. We're going to have mass of Kofi times velocity of Kofi. Yeah, that's what we're solving for, so we should know everything else. Plus mass of the skateboard times velocity of the skateboard. Right? You guys hear that? Because if you can get that far, then at this point you can just plug in numbers and solve it. Right? If that makes sense. Right, so yeah, let's do it. Let's plug in numbers and solve it. I got 50 kg on Kofi. I got 3 kg on the skateboard. And they were really, oh, whoops, I didn't tell you the initial speed, did I? Nope, I did not. So throw a number here. Maybe like 2.5, I guess, meters per second. Okay. 2.5 meters per second. A little bit different than the book number. Here's 50 kilograms again, times final velocity of Kofi. I figured that out. Then the skateboard, doesn't matter what the mass of the skateboard is, because it came to a full stop 0 meters per second. Well, it matters in the sense that it would affect the final answer, but this is like 0 units of momentum right there, right? So actually, look, we're one algebra step away from solving it. What's the one algebra step at this point? Yeah, divide by mass of Kofi. So velocity Kofi is, I got 53 kilograms on the left times 2.5 meters per second, all divided by 50 kilograms. I'm looking at 2.65 meters per second. Okay, that's relative to, let's say, a nearby tree. Something like that. Or, just the outside world in general. Okay. Now, what is this true like jumping speed? Well, you have to consider that the skateboard just moves back 2.5 meters per second. So I guess it would be this plus 2.5, or that'd be like 5 point something like that. Okay. So he can actually jump faster, but because he's pushing the skateboard back relative to the outside world, it doesn't look like he's jumping that fast. Yeah. Right, you guys good there? Right. One addition to this, I promise you guys that the kinetic energy should increase. So I'll make a little note above here. Kinetic energy initial equals, kinetic energy final equals, and let's go test it. I'll just do this on the calculator. And final kinetic energy must be more than initial because he's jumping. So let's see. Right. Got 1/2 mv squared, right? So 1/2 times 53 kilograms collectively times 2.5 meters per second squared. I'm looking at, there were originally 166 joules of energy in the system. Okay. How about after the jump? 1/2 times 50 kilograms times jumping speed squared, 2.65 squared, plus the skateboard. Oh, well, the skateboard would just be 0 because it's at rest, right? Okay. Let's see. 176 joules of energy. Yep, it definitely went up by 10 joules. Guess that? If you ran this in reverse, then the opposite would be true, which is true for inelastic collisions. Inelastic collisions, you see less kinetic energy after compared to before, because some of that energy goes to deformation, heat, that sort of thing. Okay, 86, ice hockey, a 0.115 kilogram ice hockey puck. I assume that's the regulation number. Moves at so many meters per second, and strikes a jacket of this mass that had been thrown onto the ice by a fan of a certain hockey team. The puck and jacket slide off together. Ooh, that sounds like an inelastic collision. Find their velocity. Okay. Yeah, actually, this is sort of what we just did. I mean, it's an inelastic framing like we just did, but it's even more straightforward. Yeah. So number 86. We got this hockey puck. I'll just use the mass of the hockey puck, 0.115 kilograms. Oh, this was originally sliding at V puck is, I'm going to make up a number. We'll call it 30 meters per second. Round it down a little bit from the book. It's going to collide with this jacket. Okay. Where the mass of the jacket, that's mass of the puck, here's the mass of the jacket, is, okay, I'll call it a 0.40 kilograms, just like that. Okay. Right. When they collide inelastically and slide together on that frictionless ice, how fast? Okay. Oh, this one should be real straightforward. See if you can beat me to the answer. Sum of momentum initial equals sum of momentum final, like pre-collision, post-collision. Okay. So it was mass of the puck times velocity of the puck initial plus mass of the jacket times velocity of the jacket initial, which of course was 0, so this whole piece just gonna go away. Okay. Equals the combined mass, puck plus jacket, times V final, and that's what we're trying to figure out. Okay. So numbers, the puck was this many kilograms, moving at this velocity, plus, okay, now the jacket, since it was at rest, its mass, whatever, times 0 is 0 kilogram meter per second, so it's not adding to the momentum. All the momentum is coming from the puck. Okay? Right, then after the collision, puck plus jacket, that is 0.115 kilograms plus 0.40 kilograms times the final. Okay. Do you guys see the one algebra step that's going to let you isolate V final? You have to divide both sides by the sum of the masses. Okay. So do that right here. We've got 0.115 times 30, that's the initial momentum, kilogram meter per second. Okay. Then divide that by the sum of these masses, 0.115 and 0.4. Okay. That's giving me the final is 6.70 meters per second. Guys good there? All right, so some finishing touches on this one. Do you guys see how the mass of the puck is approximately a quarter of the mass of the jacket? Not exactly, but pretty close to. So would you guys say then that the mass of the puck is approximately 1/5 of the total mass of the system, right? So the mass of the puck is about 1/5 of the mass of the whole system, right? So, hey, would that mean then that when it collides with the jacket, that the post-collision velocity should be about 1/5 of the original velocity? Right? What's 1/5 of 30? Like 6? Oh, look at that. It's pretty close, isn't it? Ooh, this is kind of a big picture short. And the other thing I want to say about this is let's compare kinetic energy before and after. Where is there going to be more kinetic energy, before the collision or after the collision? How about before? Right, well, let's test it. Right. So before, do K naught. K naught was 1/2 mv squared, so 1/2 times mass of the puck, 0.15, right, times v squared is 30 squared. Right. We're looking at 51.75 joules. I'll round that to about 52 joules. About 52 joules of energy. Kinetic final, post-collision. This number better be less than 52 joules. Let's see. So 1/2 times the combined mass, 0.115 plus 0.4, times the final velocity squared, 6.7 squared, is, well, 11.6. That's about 12 joules. Yeah, definitely a huge kinetic energy loss there. Right? Remember, the energy didn't disappear from the universe, just converted into other forms, non-mechanical forms. All right, that's going to bring us to the last question from the main homework, number 74. All right, so tell you guys what we're doing with this one. So all day today, I've been getting through about halfway through on this one. So I'll set this up for you guys, give you guys a picture. We'll start solving stuff, but probably not get to bleed into this thing. But I'll wrap this up with you guys another day. Okay? So 74, got marble C with the mass of, say, 5 grams. Maybe this is speed of 20 centimeters per second. Grams and centimeters. Hey, when you guys did your collision cart lab, had you guys using grams and centimeters, right? We don't very often, but sometimes. Collides with the second marble D that has twice as much mass. Maybe this is like the shooter, right? 10 grams versus 5, 10. Moving at half the speed, 10 centimeters per second, but in the same direction. Okay, so can you guys imagine a model where there's like a fast car that slams into a slow car? Right? That they're both moving forward, but it's like slam like that. Right? Maybe it's like ba-boing, 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 right? Something like that. Okay, so that's kind of what we're looking at. After the collision, marble C continues with the speed of only 8 centimeters per second. Remember, originally it was going 20, now it's down to 8, so it's slowed way down. But it's still going in the same direction now. Okay, kind of makes sense. All right, so this is a 5-part, question I have. Sketch the situation and identify the system. We have a 2 marble system. Okay? Identify before and after the collision. And they said set up a coordinate system, but it's just all going to be along one axis, just like the x-axis. So that's not even very fancy. We got calculate the marble's momenta before the collision. So momenta is plural of momentum. Calculate the momentum of marble C after the collision and marble D after the collision. And then finally, what is the speed of marble D after the collision? And you know what? If you just do general conservation of momentum, you could just jump straight to question E and answer that pretty much right away anyway. But yeah, they do have all these intermediary, middle step questions to ask us along the way. So at least get a picture and solution started. And so marble C has a mass of 5 grams. Okay, I'll call this maybe like mass C, something like that. So mass C is 5 grams. And it's really on the move. Looking at initial velocity of marble C. So VC initial is 20 centimeters per second. Then it's going to, bam, collide with marble D. Marble D has a mass of 10 grams, so twice as much mass. But it was only moving half the speed, but in the same direction, so half the velocity. So velocity of marble D initial was only 10 centimeters per second. Right. So this is all before the collision. Right. So I'll call this before. Then after the collision, well, think about what's happening after. Because there's some, bam, collision. And then marble C is going to continue. This isn't exactly correct how I draw it, but you guys get the idea. Right. Marble C, marble D. Marble C keeps going forward, but slowed way down. So now it's only so velocity C final, like post collision, is only 8 centimeters per second. Right? And what happened to marble D? Right? Do you guys think that marble D probably sped up because it got a little boost from behind, a little bump? Right? Well, I'm going to guess that it probably did. I mean, that would be consistent with conservation of momentum, right, for it to speed up. Right? But sped up how much? Velocity D final. Right? Right? So this is well, you could answer this right away. This would just be the answer to question E. Right? What's the speed of marble D after? Right? We're eventually ahead of it. So here's your after situation. Sort of, right? Like that. Yeah. Right. This collision, I guess, should be like in the past, right? So you guys get that collision doesn't exactly go there. So, all right. So that's question A. Here's your before and after. Okay. Question B, calculate the momentum before the collision, and then C and D, or what's going on after the collision. Right? So here, do this before you guys take off. Right. Guys, what is 5 times 20? 100. What is 10 times 10? 100. Now that's in terms of grams and centimeters and seconds. But we call it like 100 units of momentum, 100 units of momentum. Right? You guys see that there's collectively 200 units of momentum in the system? Do you guys think that after a bam, that there's still going to be collectively 200 units in the system? Like this guy's still 5 grams. This guy's still 10 grams. Right. 5 times 8 is 40. Do you think that the other 60 units have to go into here? Wait, what did I mess up here? 5 times 8 is 40. Or, sorry, 100 and, I meant, 160. There's still 160. Guys, what's 160 divided by 10? 16? Guys, so you can actually do this real fast, like once you've done so many problems. Okay, well, bell's gonna ring like any second here, so we'll call that a pause point. Tomorrow I'll let you guys work on that open notes take-home quiz, and we'll come back and wrap this one up another day.